Okay, so I'm going to break my talk into essentially 3 parts or topics. The first of which I'm going to talk about our current codes. These are theoretical physics codes, and in particular what we've done on the extreme scaling system, which is part of DIRAC for lattice QCD simulation, so a redevelopment of our code in the last 5 years. How we plan to gain portability to future hardware, which, as we've seen, will include a proliferation of possible accelerator types, etc. So obviously, these are not necessarily all solved problems. I've maybe solved some of the problems, and we'll tell you the directions we're going in, but some very much forward-looking. And then I'll talk about some work that I've done in the area of the convergence of HPC and AI requirements. Okay, so first of all, as we've heard several times, nowadays floating point is essentially free in terms of the arithmetic cost, and data motion to keep these beasts fed is actually key. So Berkeley have rightly pushed arithmetic intensity and this roofline model as the idea that chips will have a peak, and given the number of flops per byte they access, and the typical memory system being much slower than the actual floating point peak of a chip is able to access for the majority of algorithms, you end up seeing that the executed flops per second is really the flops per byte times the bytes per second, assuming saturation of the memory system bandwidth. Now, that I would criticize as being a very one-dimensional approach. It's certainly good in terms of getting the community to think in the right direction, but with more care you can categorize where data is coming from by the origin of the reference. So you can actually categorize as the bandwidth of the cache, the bandwidth of the memory, the bandwidth of the network, all of which makes for a multi-dimensional rather than one-dimensional application map as you start doing co-design. So our problem, to spare you the big equations, I thought I'd show you the floor of St. Paul's Cathedral, where Paul Dirac is buried. So I have a bad joke, but since I'm on camera here, I'll maybe not crack the joke. You can ask me at coffee break. So we have this linear differential equation. It's a nearest neighbor stencil problem, typical discretized partial differential equation, which we have to solve repeatedly in the calculation of QCD, maybe running for run times on something like 1,000 nodes for up to a year in a single calculation, checkpointing it obviously as we go along. Okay, so this nearest neighbor stencil, it's a classic, turns the problem that we have into a classic Halo exchange PDE problem, where we do in a distributed memory machine, we use MPI to transfer faces between nodes and have a subcell of space-time on each node. So this is a 2-dimensional checkerboard type approach where you can think of a series of chessboards. We're of course doing this in 4 dimensions, so it's hypercuboids rather than chessboards that we're stitching together. So we have an L to the 4th local volume per node, so if it's a chessboard, it'd be 8 by 8. And then we stitch a whole load of these together, all calculating in unison. And you can think if you're calculating a finite difference operator, so you've got a difference backwards and forwards in the x direction, backwards and forwards in the y direction, and so on, you can immediately see that 1/8 of your data, if you're on a chessboard, comes from off that chessboard. Because every time you shift by 1, 7 come locally, and the 8th comes from off node. So you can immediately see that the bandwidth you require from off node, from pure geometrical considerations, is 1/L times the bandwidth you access locally. Right, so if you know the memory bandwidth times some reuse factor for the cache that you get, because it's a stencil problem, you do have reuse, you can see the network bandwidth is actually this effective delivered cache plus memory bandwidth you get out of the local computation, divided by a modest number, where that number can be perhaps 10. So if you're pulling 600, 700, 800 gigabytes a second out of your caches, or even more, you're immediately hitting 100 gigabytes a second required from your neighboring nodes in this problem. Right, so network bandwidth is important. If you get it right, so we go back to the BlueGene I worked in the design of BlueGene, as it says in the bio and so on. We had a system where the bandwidth in the network integrated on chip was absolutely phenomenal. It was a router was integrated on chips. There was no switch in the system. You just had to connect them together like Lego connecting copper traces. The network bandwidth would actually drop when the problem fell out of cache because the network was above the L2 cache in the memory hierarchy rather than below the L2 cache. And we had a brilliantly scalable system which would scale linearly all the way up to 1.6 million cores on the Sequoia system. Okay, so to replace this, well, this slide I've moved forward since I wrote it, so I'm looking at kind of a processor landscape, but these are the sort of things we were considering when we're looking to replace the BlueGene, which was actually quite difficult even 7 years later. So we have the multi-core, many-core, we have GPU accelerators, etc., different types of memory technologies. And you can see that we have really here a massive architectural diversity between SIMD CPUs with multiple cores and many different types of accelerators, not all of which are programmable with CUDA. And we have to actually consider this in our requirements going forwards. Now, if we take the starting point of the BlueGene queue here, this is almost impossible to read. So this is the peak performance per system and the peak performance per node versus time on the horizontal axis. And you can see that we're seeing a 1, 2, 3 orders of magnitude increase in the performance per node in comparing Summit, including FP16, so these tensor cores, to the BlueGene starting point, accompanied with a 0 increase in the interconnect bandwidth, which certainly gives us problems. Things may improve hopefully in the near future with the greater I/O bandwidth in AMD Rome that we've heard about, and the possibility of multiple HFIs per node coming forwards, but we are still seeing a slightly dismal roadmap when it comes to interconnect. Okay, so with this background, the design considerations that we took when we were rewriting our QCD code from scratch starting 4 years ago, are, well, initially we had the limited target of being able to target multiple CPU architectures with SIMD vector units, OpenMP, and MPI hybrid. And we have since layered in the target to also target multiple GPUs with the SIMT, slightly different SIMT execution model, which is only superficially different if you actually think about it, but it's a real pain to program both simultaneously with the same code, plus GPU offload acceleration, primitives, and MPI. The problem we have, I've talked about checkerboards, so you'll not be surprised when I talk about n-dimensional Cartesian arrays, the possibility of multiple grids with advanced algorithms. And to do this, we program with a data parallel C++ layer where you write as if there's a single managing processor that manages the whole machine, data parallel, and you have a distributed array, but you just talk to the array container and say, add these two together, multiply this by that, etc. So it's a very much connection machine-inspired data parallel addressing scheme. This was started with Intel funding as an IPCC. We've since done GPU portability studies with US QCD, which is DOE funded, and it's now been adopted as plan of record by US QCD in the DOE exascale computing project, and the GPU port, at least for CUDA and NVIDIA, is complete. Okay, so how did we do that? Well, I would say that looking at the landscape, this is a biased view because I'm looking at a subset, but I'm looking at a subset that's actually making progress, which makes it a self-selecting set rather than bias, which is that we recognize that GPUs and CPUs with SIMD expose a granularity, the vector length, or the warp size, or the coalescence length in a GPU. These are exposed explicitly, and they're architecture dependent. So how you write optimal code depends on the architecture, and in particular the data structures, layouts have to change depending on the architecture, which creates a problem, and it particularly creates a problem because languages make guarantees about data layout if you tell it the array dimensions. So you've essentially got to optimize for something that the language contractually promises you can't optimize. right? So you have to break that assumption. So what we do is we stick our arrays inside opaque C++ containers and say you're not allowed to peek inside, right? So we're not using language arrays, we're using our own defined containers. And then we can change the layout internally. So Cocos uses something like this. I'm using something like this in Grid. And I would say that OpenMP and OpenAC address how to express where to run stuff, but they don't address the layout issues, so they don't change the language contract in terms of array layout. Regardless, there's a few packages out there, Raja, Cocos. I'm using something that's very QCD specific, but similar, using advanced C++11 features, inline header template libraries, all of this stuff to opaquify the array layouts and then optimize them. Obviously, you can write C++ to be arbitrarily inefficient. It's quite easy to do so. It almost encourages you to do so. You've got to sit in your hands and use a strict subset of the language that inlines and gets removed. And if you don't, it just runs, it just sucks. Okay, so we hide the data layout, and then the final key feature is that we wrap parallel loops in a macro. I wrap it in a macro. Some people use inline functions, but you capture that loop body in a little implicitly created object called a device lambda that was introduced for C++11 and extended with CUDA. So you capture a lambda function that you can then say run this on the device. Okay, and then with different primitives, because I've wrapped this in a macro, I can change the macro to expand to an OpenMP loop in one architecture, or to expand to a CUDA kernel call in a different architecture or whatever. Right, so that's kind of the key trick to what I'm doing with Grid. So as I've said, the layout that's optimal depends on the architecture. So we all knew that microprocessor order has all the scalar stuff inside. Vector order has big arrays in the innermost dimension, and the outermost guys contain the sort of detailed little structures and so on, so you get contiguous access. And of course, on SIMD and GPUs, you're actually best to use some kind of array of struct of array, people will call it, but what I would call an array of structs of short vectors. Okay? So that you have a granule that's the vector length of the architecture, it's the width of a warp or whatever. These are contiguously accessed, coalesce in a GPU, give you nice aligned loads in a CPU. But then the rest of it is in a cache-friendly microprocessor order outside that, and so on. So, and the point is to then abstract it away and hide it, where we introduce these lattice containers. This happens to be something called a color matrix. That's a grid of something that's a color matrix per site. And you then write in a high-level C equals A star B type data parallel form, where over every element of this grid, it does the same operation in a data parallel way. And this will program a full MPI domain decomposed calculation that way, so you end up with a high-level interface. High-level code, we're getting 65% of peak in AVX2, for example, from L2 cache. And we are using a single way of expressing our parallelism that's targeting both CPU and GPU, SIMD and threads, etc., efficiently. The other thing that's worth mentioning is there's a really nice C++11 expression template engine that's only 400 lines of code. It's very dense code, but if you compare to the US QCD package that we're aiming to replace, that had 10 to the 5 lines of machine-generated code to generate the same functionality, actually less efficient, less complete functionality than I've got. So advanced language features in C++ are actually worth looking into. Okay, so in more detail, memory layout. So if you might declare one of our arrays, say the spinner array, as a 4x3 matrix if you want. And in a scalar code, traditional scalar CPU would represent it in memory as a 4x3 array, and within a thread as a 4x3 array. If you were talking to a SIMD CPU architecture, the register file would contain SIMD vectors, so you would have a 4x3 by n array after you've done a structive array transformation, and that would be present both, what I say, in the thread, i.e. on the stack, and in the memory, it would be represented the same. The difference with GPUs is that when you do an access, each thread corresponds to one SIMD lane of these n. So you represent it in memory with this structive array transformed data, but each stack variable has to be 4x3, like a scalar layout. So you have to do a transformation that's different. And you have to write, I've structured this now to write the code in a way where I can target both of these at the same time with the same code. And the trick is I use an operator parentheses to transform from memory layout to per thread layout, so that if I'm on a GPU architecture, it compactifies, if you want, this memory resident variable into a scalar laid out variable, but on a GPU, operator bracket doesn't do that compactification and leaves you with MM512 or MM256 type objects, with the result that we can write code, so long as the code uses the return type of this operator bracket, it figures out what to do according to the architecture, which is quite cute, actually. Okay, so for example, if we take the original code that ran very efficiently in this SIMD vector CPU, where I have something like A equals B plus C for each element of some distributed container, that then becomes a coalesced write to the output vector with B parenthesis, C parenthesis, which then does these coalesced reads. An intermediate goes to a scalar representation and then goes back to a vector representation when it does the write to memory. So this is not a hugely destructive change to make globally in a code. So it only took me a month, right? So getting this, after doing this, we then have code that runs essentially unmodified in the CPU target, but now also picks up the SIMT execution model in the GPU target, which I think is quite cute. So I can go into some details, but basically you see at some point I have if we are in a SIMT target, do one thing, else do another thing for operator bracket. And then when we write stuff, write code, we can use the return type of this operator bracket to figure out what we're doing. So for example, we can use a decal type. So we can basically type def the type that is returned by something that does a coalesce read to be a new type. And then providing we use that new type here, which we do, so we have temporaries temp1 and temp2, the return type of coalesce read is dictating what is the internal per thread stack resident data type, and that's changing from vector to in a CPU to scalar in a GPU automatically and doing the right thing in all cases. So we have a single source code that is giving good performance everywhere. So some benchmark figures. So everyone's going to look at this now and go, oh, he's only getting 10% of peak. That sucks. Believe me, this is very difficult to obtain these days, right? So we're getting, 10 to 15, even 20% of peak, depending on the architecture. Doing very well in Zen 1, so this is the original, the Naples rather than Rome here, actually already almost matching a Skylake with that. So we're doing very well, and then the key point here is that we're getting still 10% of peak on the GPU at the bottom now. This is new as of this year. That's maybe 80 or 90% of the CUDA code that NVIDIA releases, right? So we're doing well with single source code. We've got performance portability without having to write special code that only works in one architecture through this. Some little comments. We're running on Epic, on the original Naples, we're running 1 MPI rank per die. It's a multi-die module, and then using shared memory between the dies so that we have threads, and we're using hybrid threading, so we run threads within a NUMA domain, shared memory between NUMA domains. All the threads, I throw MPI in the bin because MPI is a single threaded interface, and use all the threads to copy through shared memory to each other. And I only drop to MPI to go off the node at that point, which is how I managed to get really good scaling, even in the Naples, for example. Okay, so we've done CUDA. We're using unified virtual memory. That's what it says in the tin. It works. You can't bother with copy to device and back again. If it's on the device, you've used it recently, it'll stay on the device. Runs with good performance. And we're considering OpenMP5 and SYCL for AMD and Intel portability later. Now, some further hacks and exploits, whatever, to get good performance in these systems. So as I've said, on multi-C socket servers, we're using 1 MPI rank per NUMA domain. We use threading within a NUMA domain. Why? Because the access is uniform, so you might as well copy it once, read it once, rather than copying it across, putting it somewhere else, and then accessing it. You're always somehow intrinsically faster to use threading where the memory access is uniform. We ditch MPI when it comes, we use MPI to tell us which ranks are on the same node, but we then ditch it for copying within the node because we can use threading to go have all cores copying across the UPI. This involves a little bit of trickery to trick MPI cart create to do the right thing. We actually construct our own communicators to trick MPI cart create so that we can stack our MPI ranks within a node in the maximally cubical form. So we maximize the number of interior faces and minimize the communications that goes between ranks off node. Okay, so we have this clever trick. It then turned out that exactly the same trick we're using to maximize comms over UPI within a multi-socket server with no new routines, just changing the implementation, worked going over NVLink between multiple GPUs, where we use peer-to-peer over NVLink with exactly the same logic to maximize intranode stuff in Summit, for example. Next stage of locality is in the network. We played with a great project with James Southern at SGI, where we looked at their hypercube approach. We have used these Cartesian problems, we've used BlueGenes for ages. We love 3D networks, 4D networks, 5D networks, etc. We had to look at the hypercube and realize that we can embed any lower dimensional torus we want inside a sensible power of 2 hypercube machine. So this is I think a 2 to the 8 hypercube drawn graphically, schematically. And what I'm showing here is there's little red squares and a little green meandering connected path showing that you can map a 2-dimensional subtorus in an 8-dimensional hypercube in a way that it's always nearest neighbor in terms of its connectivity, with the result that you don't share the bandwidth in any link. So you can live with the non-full bisection bandwidth in this system and get perfect scalability all the way up to a system much bigger than the largest director switch you can buy. So we get full connectivity without buying anything other than edge switches in this system, which is quite cute. And you can see, compared to standard MPI cart create in Cheyenne at NCAR, with my communicator, not MPI's Cartesian communicator, you get a factor of 4 speed up in halo exchange on the largest system sizes. And when you stay within a switch, you get, of course, just a factor of 1 because it's the same speed. So locality. So with that, we bought one, installed it as the extreme scaling system in Edinburgh in March 2018, upgraded it in 2019, so we have something like 1,400 nodes running here, where you can see once we go to 16 nodes, you continue to get weak scaling and the perfect weak scaling and the performance, so there's no slowdown as we go higher. On 512 nodes, I've benchmarked that we're running all links in that system at 19 out of a possible 25 gigabytes a second, send plus receive added together. 76% of wire speed on every single link in the system concurrently, which is quite nice. And you can see that the drop-off compared to the single node performance is not great, so we're not over-speccing the node compared to the network here. Okay, so we were happy customers. I'm now going to segue into the overlap between our clearly large bandwidth requirements with this problem and AI. So I asked the question, what do fundamental physics and AI have in common? Of course, the answer is nothing, right? Except nothing in terms of the actual problem. But if you look at the technical solutions to our problems, we both have a strong scaling problem where we have obviously enormous floating point requirements, but we're seeking to distribute and accelerate a tightly coupled problem that has a large number of serial steps. In AI, you're constantly calculating a gradient on as smaller problem as possible, spread out as much as possible, because you want the stochastic gradient descent with a small mini batch size, and then summing it across a machine and taking a forward step, doing the same again, compute, calculate a gradient, big reduction, forward step. We're doing a Markov chain Monte Carlo, where we do a sparse matrix inversion, forward step in Monte Carlo time, sparse matrix, etc., etc. So it's fairly similar, actually, at a coarse computational level, even if the actual problem is completely different. So the point being that AI therefore has distributed compute trying to be applied to a small problem size, and then reduce that result across the machine with a large vector reduction, multi-megabyte packet, and repeat. Okay? So we are both therefore desperately seeking bandwidth. We have a collaboration. As I said, we started out with an IPCC and have an ongoing collaboration with Intel and Brookhaven Labs, who had, I think, probably one of the only dual-rail Knights Landing plus OPA systems in the world. And Knights Landing does not have a particularly great processor core. OPA has some CPU overhead. We initially found that we could saturate a single rail with OPA, but we couldn't saturate the bandwidth of dual rail with OPA, especially when we're running this hybrid OpenMP plus MPI model. Now, on top of that, we also discovered we were seeing very surprising factor of 100 slowdown performance brittleness in what we were getting in terms of the delivered network bandwidth. We tracked the big drops eventually to the occurrence of page fragmentation and small pages occurring despite Linux's THP, and fixed that by allocating explicit huge pages. There are various ways to do that, but there's a what's the library? There's a huge TLBFS library that you can link that will help you with that, and I think all sites should start using that. So getting huge pages, we've got performance reliability. We then persuaded Intel to update their MPI library with a patch which is becoming increasingly mainstream, where it will allow different threads to re-enter the MPI stack concurrently, providing they're entering different communicators rather than having a global lock on the MPI stack. With the result, you can throw 2, 4, 8, however many cores you want into driving the MPI hardware, into driving the interconnect hardware concurrently, which will bring us then up from the blue to the red curve here, saturating 44 out of a possible 50 gigabytes a second of bidirectional bandwidth, after we have our code changes paired with Intel's MPI stack changes, which is a really nice result. Now, Baidu have a similar problem. They very proudly published the ring all reduce code, bringing HPC techniques to deep learning, which was this purple curve here. So we decided to have a bit of fun and go and speed up their code with the same techniques that we would develop with our QCD code, because fundamentally we're just shunting bytes over the network. So in the end, we rose from something like 7 gigabytes a second bidirectional send and receive in the all reduce. This is with a single MPI rank per node trying to drive it, to 35 gigabytes a second send plus receive from each node added together in the ring all reduce once we'd finished with it. So that was an interesting case of crossover between HPC techniques and AI techniques. And I think and even then, if you forget to do the huge page thing, you still see unpredictable drops, right? So huge pages remain important. Finally, I'm going to look at SIMT. So I've made the bold claim that just adding floating point doesn't help our problem if you don't also balance it with network, with interconnect. SIMT has 6 very fast voltage GPUs and 2 admittedly great EDR cards, but they're not exactly balanced with the level of floating point, as you see from the starting point of BlueGene, where the network's no faster, but we're a factor of 100 faster in the compute node. So this was using the NVIDIA CUDA code, and my code is now similar. And you can see the performance in a single node all the way up to 6 GPUs. The performance per GPU is scaling pretty well within the node, internode. But the moment you go beyond 1 node to 2 nodes, you drop by a big factor. By the time you hit 8 nodes, you have fallen off by a long shot on SIMT. And that clearly is associated with the network bandwidth not keeping up with the phenomenal local floating point for this particular problem. Second element of crossover between our projects and AI. Another thing that I've done for my sins has been the co-design leader of the Intel ATI strategic partnership. Some element of that has been working with Sid Kashyap and Angus Lepper, who are Intel engineers, formerly DIRAC RSEs hired by Intel. And as part of this, we brought the GNU multi-precision stuff that we've done. We've been using GMP for a while for precision sensitive parts of our code. We decided to do a systematic study of machine learning problems, so classic SciFAR, ResNet, blah blah blah, etc. try a whole suite of them, back-ending them with an LD preload library and substituting the matrix multiply with a reduced precision matrix multiply, where we could choose how many mantissa and exponent bits there were and turn them like dials and see how the thing converged. So we could try all possible cases down to 11 bits. We didn't try pi bits of floating point, but transcendental number, but all integer number of bits we could try and see how it does. And we were able to compare IEEE FP16 to FP32 and a modified FP16 that had more exponent bits and fewer mantissa bits, so this S7E8 in terms of the significand and exponent. And we discovered that a non-IEEE FP16 was more stable, and in fact this was exactly what Google has been using as a software floating point, 16-bit floating point inside their TensorFlow library. So this we submitted as a patent, crossed over. I guess beyond empiricism, we histogrammed the results of every multiply, and you can see that the range of results was big enough that you weren't covering them with the exponent range of FP16 IEEE, but you do just about cover it in terms of the gradient sizes evaluations with the modified format, which is why this behaved like FP32, because it could cover the full exponent range of the data it was hitting, whereas FP16 would be rounding to 0, would be denormaling and flushing to 0 as you go beyond that. Okay, so lessons learned. So just to summarize then, I would say that lessons learned from all of this huge effort, it's been 18 months doing a GPU port of this already efficient SIMD CPU multi-core code. Lessons I would take home if I was going to look at another code: advanced C++ can give faster than Fortran performance if used judiciously, right? Template metaprogramming and so on, it's painful, scientists grumble when you ask them to do it, but you can insert all of this stuff very flexibly and remove things at compile time and generate very efficient vector code by design. I'm using macros, and you can hash define underscore something to be underscore pragma. So you can stick a pragma like an offload OpenMP or OpenAC offload pragma through a macro, so you can change it later. So it only has to occur at one place in your code and make a global substitution as you change the compile target. So capturing loop bodies in macros and dressing the pragmas through a preprocessor system is helpful to portability, because you can change the pragmas according to what you're compiling for, right? So you shouldn't be sticking naked pragmas all over your code in 1,000 different places, because you can't edit that later. Whereas if you have them in a single header file, you can change it later. So abstracting the parallel primitives makes sense, because you can back-end it and redirect it, right? So long as you're consistent and do this globally through your code. Capture the parallel loop bodies in the macro. Store the memory arrays in an opaque template container so that you can change the layout. If you make no promises about the layout, you don't break any promises when you change it, right? Language standard arrays make promises which prevent you from changing it. Finally, I'm using a per thread accessor to translate between memory resident and thread stack resident format. That is the identity mapping on a CPU. So what you get from memory is what you process inside the CPU, but on a GPU, what you get from memory is a vectorized object, and what you get inside the GPU thread is a scalarized object. So by going through these accessors and using the type returned by these accessors to determine all the internal types in the parallel loops, you then can accommodate the difference between SIMT and SIMD without rewriting code, right? You have a single common code base. You have to change the code clearly, but you can then, after you've changed it, you have a common code base that works everywhere, and therefore that decreases maintenance going forwards. And then finally, Dream Machine. What would I like to see then as the potential replacer for DIRAC? I aim to have potentially accelerated nodes, a 1-to-1 ratio between accelerators and 100 gigabit class HFIs. All the Cray slingshot systems planned for the US look promising. I would avoid this would avoid some interconnect cliff that I've shown you, I think, quite clearly that we hit, because we're scaling up the bandwidth more as we add floating point. It would avoid, we certainly want to avoid lock-in to any one accelerator vendor and indeed any one interconnect vendor, right? We want to be able to mix and match parts and have a one-to-one ratio as we mix and match those parts. Wrapping acceleration primitives is key, right? If we're going to be smart buyers, we have to be able to buy anything. So you engender competition, and that applies at every single component in the system. I think that I'm currently targeting CUDA with what I've done. I'm hoping to target OpenMP5. I'm also hoping to target SYCL. OpenMP5, I think, is critical to making this kind of acceleration generally usable to the broad scientific community. I believe the US is investing heavily in OpenMP5. In fact, I think they're betting billions of dollars on OpenMP5 and write once, run everywhere. We can change the accelerator types, and because there's multiple accelerator types in their program. There's NVIDIA types in Perlmutter, there's AMD types, there's Intel types coming forwards. So having a single software base that runs on all of these is going to be important for them. So I would personally bet on OpenMP5 acceleration. With the caveat that OpenMP5 does not actually address this data layout problem that I was talking about, right? So you've got to still think about that in your code in addition to porting the acceleration primitives through OpenMP5. So I would actually say broadly that the ideal QCD machine and the ideal AI training machine, where you have to do the stochastic gradient descent and do the very fast reduction of the gradients, actually have very similar requirements. We have a huge floating point requirement satisfied with accelerators, but we have a massive interconnect requirement to enable the thing to scale on a non-trivial tightly coupled problem. So at that point, I'm finished, even though I'm 10 minutes early.